Okay, now let's continue with our next chapter. Next topic. Okay, which is electric flux density. All right. So for this chapter, for this topic, again, I hope for you to put around 60 minutes. Okay, for this lecture. All right, and after that, you will proceed with the practice of that I have provided inside the e-learning. Okay, and now let's look what we will learn in this topic. Okay, we will learn about the electric flux density and also the application of Gauss law to calculate the electric field intensity for asymmetric charge distributions. All right, and here are the keywords for your reference. Okay, so let's have a few revision. Okay, from what we have learned before. And before we have learned about the stationary charge, okay, stationary charge, and I think usually you already know this stationary charge. The symbol is denoted as Q. However, in this slide, I put it as rho V. Uh, to assume, okay, that the point charge, which is Q, okay, can also be can be put inside a volume charge. All right, and the same goes to the line charge, also can be filled in volume charge, and also surface charge also can be filled in volume charge as well, and that's why I make it as rho V. Okay, so please don't confuse it. It is actually Q, but only for this topic I make it as rho V. Okay. Okay, and from previous, okay, we have learned about Coulomb's law, all right, where based from this formula, okay, where E, which is the electric field intensity, is equals to the force, yeah, F over Q, okay, where Q in this particular topic, I write it as rho V, right? And from here, from stationary charge, we can denote or we can determine the electric field intensity, right, through Coulomb's law. Okay, what are the other parameters that we can obtain from this stationary charge? If you refer to the Sadiko books, if you already have these Sadiko books, okay, you may refer to topic 4.5. Yeah, you may refer to the topic 4.5 under the topic of electric flux density, or if you have any reference book of electromagnetics, okay, please read those reference book as well. All right. Okay, so now let's look from this stationary charge, what can be determined, what other parameters can be determined, all right? So from this stationary charge, we can also determine electric flux, and we can also determine electric flux density. Okay, these are the two points that we will look today. All right, so let's look first about the electric flux. All right, so here are the symbol of electric flux. Okay, it is written as this. Okay, based on Faraday. Okay, based on Faraday, electric flux is a number of lines coming from electric source. Okay, so it is just a number of lines coming from electric source without any direction. So this electric flux is a scalar. It is represented in terms of scalar. Right, it has only magnitudes without any direction. So let's we look into details. What are this Faraday meant by this sentence? Okay, so for example, we have three different point charge here. Okay, each point charge have different value of charge. For example, the blue charge have 3 columns, the orange have 5 columns, and the green have 8 columns. Alright, since Faraday mentioned that electric flux is number of lines coming from electric source, so here are the electric source. Okay, so here are the point source or the electric source. So there will be electric flux is a number of lines. So there will be a number of lines coming from this source. So for example, for this 3 charge electric source, it will produce 3 lines of electric flux. it will produce three lines, and these lines is known as electric flux. Right? So for 5-point charge, it will produce 5 lines of electric source. Of electric flux. Right? So I think by now you already have the idea for what will happen for this 8-point charge. It will produce how many? It will produce 8 lines of electric flux. Alright? So if you want to compare each of these point charges, okay, all these point charges should have same unit, which is each of them should have column, okay, same unit column. Then only you can compare with all these 3-point charges. All right, and if you look at the what diagram here, what can you see more? You can say that for this 8-point charge, it will produce, it has higher it has higher magnitude. It has higher magnitude compared to the blue charge and the orange charge. Why did we say so? It is because the lines coming out from this electric source is more compared to the line that coming from the blue source, the blue electric source and the orange electric source. So that's why it has higher magnitude. So based on what has Faraday, the definition of Faraday here, we can rewrite that the electric flux equal to the magnitude of the charge, of particular charge. So electric flux is equals to the Q. Alright, we can write it as this. Okay, from here, okay, from this point charge, okay, and this electric flux, let's discuss what is electric flux density. Okay, so electric flux density, we have, for example, we have the point charge and also the electric flux. Okay, this is the electrics. The lines here denote as electric flux. Okay, so here is the electric flux. I wrote it here, yeah, electric flux. Okay, so let's say that we want to find the density, the electric flux density at this point, the point Q here. So I wrote it as Q, all right, and inside this point Q, all right, inside this point Q, there is a limit. I make it limit in order to determine the electric flux density. Okay, at this point Q, from the point charge, from the point electric source, I make it a limit here. All right. So from this limit, the gray area is the limit. Inside this limit, it contains, okay, at this particular area, it contains several or a part of electric flux from this line. Okay, there is electric flux from this line that contains inside this area, only a part of electric flux from this line that contains inside this area. So therefore, I wrote the electric flux as d electric flux. It means that only a part of electric flux from this particular line contains inside this area, contains inside this particular or our interested flux, that electric flux density area. Okay, so this area I make it as a gray color here, right? So this area, it will be our limit for this sample. Okay, we will only take into consideration the area around this sample. Okay, so from here we can say that in order to calculate or to define the electric flux density, it will be the number of flux line divided by the sample area, the size of the sample area here. All right. So in order to calculate, or we can rewrite this equation. We can rewrite this equation as the difference of flux line equal to Okay, the density, the electric flux density times with sample area. However, if you look at the mathematical terms here, you can see that this, yeah, electric flux density and is in terms of a vector. Why? Okay, so I have mentioned before that the electric flux, okay, I have mentioned before that the electric flux is represent in terms of scalar, right? So in order to get or to make this flux line as scalar, and we know that this surface or this sample area is depending on the position of this electric flux density. So it means that if this electric flux density if is moved to this particular area, so the sample area will be moved at this area as well, right? So it means that this sample area have the direction. Of course, the sample area have the direction, right? So in terms to validate the math in order to represent the electric flux as a scalar, the flux density also should be represented as as a vector. Okay, so it will be the dot product of vector flux density, okay, with the sample area, the vector of sample area, we will obtain the flux line, okay, of the particular at the particular electric flux density. All right, and we can rewrite it as this equation. Okay, flux line is equals to integral of dot product electric flux density with the sample area. All right, and which is both is vector. All right. Okay, now okay, so now let's revise what we have learned previously. Okay, so from the stationary charge, we know through Coulomb's law we can obtain electric field intensity, and also I have mentioned we can also obtain the electric flux from the stationary charge through Faraday law, which is represented as this symbol, right? Now let's look some example. Okay. So let's look, for example, here, okay, where from the electric flux, we can actually define the electric flux density, where this, where which is from electric flux, we can actually define the electric flux density, okay, by using this particular formula. Right now, let's look at the example for this. Yeah. Okay. So let's look the example. Find the electric flux density, which is represented as D, okay, vector D, emanating from a point charge of Q. Okay, this is the value, the Q, where the unit is column, at the origin at an imaginary concentric sphere. Okay, it is a concentric sphere of radius r meter. Okay, now if you look at the EMT equations, usually it will not come with a diagram or lots of information. So what you have to do is, in order to solve this equation, you need to find you need to try to visualize the equation and try to get as many as information that you can get from the equations. Right, so from here, let's visualize. Okay, so here they said that there is an electric flux density. Okay, you need to find the electric flux density. So this is what your aim or your goal, to find the electric flux density. And they said that it is emanating from a point charge. So there is a point charge. Where is the location of this point charge? It is at the origin. So there is a point charge which is located at the origin of the axis, okay, which is it at an imaginary concentric sphere. So there is a concentric sphere here. So there is a sphere here. And what are the information about this sphere? It is the radius is r meter. So from the point charge to the sphere, the radius is r. Okay, and at the what and you need to find the electric flux density at the surface, right? In this sphere, all right. So as I mentioned, okay, here it also mentions sphere. So what will come in your mind should automatically spherical coordinate system that we have learned in orthogonal coordinate system. Okay, so the best or the wise the wise method is to use the spherical coordinate system, which is same as the object mentioned in the questions. And also what we need to find, we need to find the density, electric flux density, which is generated by Q. Okay, so I make it the point as point X here. Okay, and I limit the sample area. I make it the sample area as the box here. Okay, where it contains some electric flux at this particular X area here. Okay, so this sample has same direction with with R here. Yeah, with R axis. Okay, where it has since that it is what depending on it as sorry since that it is based from the direction of the r axis. Okay, so this sample area have direction in r. So since that we know that the formula is electric flux is equals to integral, there is a circle here, d which is the electric flux density dot product with the sample area. Okay, so first of all, what are the meaning of this close here? This circle here, this circle means it is a closed area. Our object that we will deal with, that we want to deal with, should be in a closed area. Okay, where the flux where the flux contains inside the sphere. Okay, we will not consider flux, that there is no flux that uh, will be produced outside this sphere. Okay, the flux of the electric flux will be produced only inside of this sphere. So that's why it is a closed area. Okay, and it is completely a closed structure, and that's why it is a circle or the circle here. All right, so now d and then ds. Now the information here, sorry, I think it's better for me to erase this so that it will not cover here. Yeah, okay, all right. So now the ds here is based on sphere coordinate system. So we know that spherical coordinate system has three variables, which is r, theta, and phi, right? So based on the surface area, okay, since that it is a surface, okay, it is a closed surface, so this is a closed we will deal with the surface formula for spherical coordinate system. So there is three direction for surface formula, which is r direction, theta direction, and phi direction. Okay, I hope that you can recall back. Okay, if you're not sure, you can refer back to the notes or the lecture previous. Okay, the previous lecture. Okay, so now which formula that we should choose? R direction, theta direction, or phi direction? So since that I have mentioned that this particular X sample has same direction in R, so the formula for ds of spherical coordinate system that we should choose, which is the one that contains the R direction. So it will be R squared sine theta d theta d phi at R direction. Okay, so I hope up until here it's clear. Alright, so now let's move to this electric flux density. So electric flux density, there is not much. Okay, we have not much information that we can get from these particular equations. So let's represent it in a general representation. Okay, so let's represent it in a general representation. So it should be dr at r direction, d theta at theta direction, and d phi at phi direction, right? Since that we are dealing with these three variables, right? So now, and we know that ds is in r direction, right? So now, okay, the formula is electric flux integral this d with ds. So it means that this d, which is dr, okay, where it is in r direction. So dr, okay, times ds, which is r squared sine theta d theta d phi at r direction, okay, dot with another r direction here, which is here, okay. One r direction is from this ds and another r direction is from here. So r direction dot product with r direction plus with d theta r squared sine theta d theta d phi r direction from this ds, and then theta direction based from this general representation, which is theta direction. And same goes to terms, the third term, yeah. So it will be phi direction times with r direction. Okay, now if we look here, this r direction times r direction, okay, is equals to 1. Why? In orthogonal coordinate system, all other axes, if you still remember, is 90 degrees, right? Where the r, where the theta, sorry, where the theta and where the phi are all orthogonal, are normal to each other. So it is 90 degrees. So r theta and r theta, so it means that it has the same direction. So it will produce 1. Okay, it will be 1. However, for theta direction and r direction, so it means that theta direction and r direction is 90 degrees to each other. So cos 90 degrees will produce as 0, okay, due to angle, if the angle is 90, which is normal to each other lah. So same goes for phi direction and r direction, it will also produce 0. So in that case, it will leave that this second term and third term as 0, and this first term will leave as drr squared sine theta d theta d phi. Okay, if you look here at this first term, there are two variables that you need to deal with, which is theta and phi. So you should solve with double integrations. Okay, so first the limit for theta. So the limit for theta is theta from 0 to pi, and then the limit for phi, which is phi from 0 to 2 pi. Okay, and if you solve this equation, you will get the electric flux. For this, okay, it will be dr 4 pi r squared. Okay, and okay, and okay, from here, since that we need to define this dr, right? We need to find this dr. So we have to rearrange or rewrite this equation. So it will be dr equals to flux line over 4 pi r squared. However, we can't use this flux line because this symbol is not given inside this question, right? But from Faraday law, okay, we have discussed that this flux line is equal to the amount of charge, which is Q. So this can rewrite as Q. Okay, we can replace this with Q, right? And since that it is moving in R direction, so we can just put S here as R direction. Okay, so from here we can say that from the point source, we can also solve, or we can also determine the electric flux density. We can also determine electric flux density by using flux line, right? By using flux line. Okay, and here we can conclude that, okay, from what we have learned in previous week and also in this topic, we can conclude that, okay, from this stationary charge, okay, based on Coulomb's law, we can solve or we can get the electric field intensity, okay, electric field intensity, and also we can also use or we can obtain the electric flux, okay, by Faraday law. And this electric flux we can also obtain, okay, from this stationary charge, we can also obtain the electric field intensity, where it will give this formula, right? And if you can recall again, okay, this electric field intensity, this electric field density can also be obtained, can be obtained by Coulomb's law, okay, through multiply this electric field intensity with epsilon naught, okay, you will get electric field density. And also from what we have discussed just now, okay, based from the flux, electric flux, we can also get the electric field density, electric flux density by using this formula. Okay, so if you solve if you are dealing with this formula, the one that you will solve is electric flux density, because you are dealing with a flux line. Okay, if you are using this formula from Coulomb's law, you will obtain the electric field density. Okay, the one that you will obtain is you will obtain the electric field density because you are solving the electric field density from the electric field intensity. Okay, this is electric field intensity, right? Intensity, and this is electric flux. Okay, so the difference is only the terms. Okay, the difference is only the terms, but it will produce the same formula. Okay, if you solve from Coulomb's law, it will be electric field density, and if you solve from this Faraday law, you will uh, uh, it will be electric flux density. Okay, and this one is the one that we call Gauss law. This one is the what that we call as Gauss law. So how, which direction, which law that you want to use to solve this electric field density. Okay, for example, you want to derive from this Coulomb law towards this, or you want to go straight away using Gauss law, or you want to use Faraday law. It depends on the situation, it depends on the application, and it depends on the questions, okay, the information that given in your questions. So now let's look into detail what is Gauss law. Okay, let's look into detail, and let's compare this Gauss law and this Coulomb's law. Yeah, because Faraday law is very easy. It's just flux line is equals to Q. However, Coulomb's law, you need lots of integration, you need lots of differentiation, and also some Gauss law. Yeah, even though it will not be as lot as Coulomb's law, right? So let's look when you want to use Coulomb's law, or when you want to use Gauss law, where you can straight away find the electric field density, right? Okay, so if you are using from the stationary charge, you are using Coulomb's law, you will obtain the electric field intensity. From this electric field intensity, then only you can get this by time or multiply with epsilon naught, then only you will derive the electric field density, right? However, if you are dealing with Gauss law, you will straight away get the electric field density. Alright, so if you look at the mathematical wise or the direction, you can see that Gauss law is much more simpler, right? It will be, you can automatically straight away derive the electric field density. However, if you are going or you are solving through Coulomb's law, it will take lots of calculation where you need to derive the electric field intensity first. After that, from there, you need to multiply with epsilon naught, then only you will get the electric field density. So if you look here, Coulomb law is much complex. However, although it is complex, it can be applied for all cases. Okay, it is possible for all cases. There is no limit for this Coulomb's law. All right, although the steps is quite lengthy. However, for this Gauss law, although it is simple, okay, if you look here, it is simple. However, it can't be applied for all cases. There is always a limit for Gauss law. Okay, let's see when or in what situation we can use this Gauss law. Okay, you can use Gauss law if the point source, okay, the source is a point charge. You can use Gauss law. If the source is line charge, you can use Gauss law if the line charge is infinite line charge. Okay, and same goes to surface charge. If the surface charge is infinite surface charge, then only you can use Gauss law. So if it is a finite line charge, can you use Gauss law? No, you can't. So if finite surface charge, can you use Gauss law? No, you can't. So please look at this. But what rules? First, before you want to decide either you want to use Gauss law or you want to use Coulomb law. Okay, Coulomb's law. And for volume charge, if you want to define a volume charge, okay, you can always use Gauss law. Okay, for volume charge, I think it's very simple. You can straight away use Gauss law. Okay, without passing through Coulomb's law first. All right. So these are the rules, and please remember these rules. All right. So now let's look into detail what is Gauss law. So Gauss law, is defined by the total electric flux, which is the line, passing through any closed imaginary surface, enclosing the charge Q is equal to Q in the SI unit. So what does that mean? Let's visualize it, I think. By reading the sentence, I think it's quite complicated to understand. So let's visualize it. So for example, let's say that we have these three different point charge, which is Q1, Q2, and Q3. Okay, this different point charge, and you have electric field density at this point at X, and you need to find the electric field density at this point. So what you need to do, if you look at the definition here, they said that electric flux passing through any closed imaginary surface. So you need to have this imaginary surface. So for example, I make my imaginary surface like this. This is my imaginary surface. This imaginary surface is known as Gaussian profile. It is known as Gaussian profile. So what is Gaussian profile? Gaussian profile is an imaginary area based on location T. So let's say that your location is pointed here. So it means that you have to make your imaginary surface that passing through this point. Okay, so it must passing through, or it must based on the location of this. Okay, and this line, this Gaussian profile should completely close. It can't be open. It should be closed. All right, and then it contains the charge. Okay, it closes the charge. All right, so now we based from the formula that we have learned before, okay, the Q, okay, is equals to integral, close integral, dot product of electric field density with the sample area. Okay, the sample area. So let's define this equation. So this is actually this equation is actually it based on the shape of Gaussian profile that you draw. Okay, so if you want to make the Gaussian profile, make sure that you choose the shape that is simple. Okay, for example, a box, a circle, a sphere. Okay, that shape is easy or simpler to be solved. Okay, avoid an ununiform shape. Okay, these are the rules. Yeah, avoid ununiform shape, since that this shape is within your control. You are the one who decide the shape, so please decide to use the shape as simple as possible. Alright, and this Q enclosed, what does that mean? It means that the Q that you will consider is the one that contains inside this Gaussian law. So in this diagram, should you consider Q3? Yes or no? No, you shouldn't. You should ignore this Q3 because it is located outside the Gaussian profile. So this Q will not be counted inside your calculation. Alright? So please be aware for that. Yeah. So your Gaussian profile will be Q1 plus Q2. Okay, sorry. In your calculation, you will take into account, you will count it Q1 charge at point 1 and charge at point 2. Okay, the sum of charge at point 1 and charge at point 2, and ignore the charge at point 3. Alright, so now let's look to the questions. Yeah, example 2. Okay, the question said that a spherical volume of radius A contains a uniform volume charge density rho v, and you need to determine the electric field density in all regions. Okay, so first thing first, what you need to do is you need to visualize the equations. So they said that there is a spherical volume. Okay, there is a spherical volume. What are the radius? The radius is A. Okay, and the shape is uniform. So it means that all the shape has same radius. Okay, it has a uniform shape. So it means that the radius is constant. Alright, the radius is constant with A. And then this sphere has the volume where it is rho v. Okay, these are the volume rho v, and what you need to find, you need to define, or you need to derive the electric field density and in all regions. So what you need, which formula that you can use, since that it is clearly mentioned a volume charge, and if you look back to the law to use Gauss law, volume charge is allowed. So straight away you can use Gauss law to solve this equation. Okay, so let's use Gauss law. Okay, you can use Gauss law, and then what are the coordinate that you uh, will deal with? Okay, what are the orthogonal coordinate system that you will deal? Since that it is a sphere, the best orthogonal coordinate system that you will use is spherical coordinate, right? Since that the source is spherical. Okay, and another information that you can get from this question is you need to determine the electric field density in all regions. So it means that you should take into consideration the one that is inside and also outside. Inside and outside. So there will be two regions that you will deal with. Okay, now let's look one by one. Let's do one by one. Okay, so let's solve the one that is inside the spherical. So the one that is inside the spherical, I make the electric field, the point of electric, the point is at this point. Okay, the sample is this sample. I note it as X. And then what should I do next is I should draw the Gaussian profile. So I draw the Gaussian profile with radius R. There should be uniform radius as well. Okay, I make it as uniform so that I deal with a simple structure, simple shape, right? So I make it as a sphere as well. Okay, with a radius R. Okay, and okay, so I denote it as region 1, which is inside the sphere. And this region 1, okay, and this calculation is true when the radius of this Gaussian profile is less than the radius of this sphere. Okay, so this calculation is not true or is not applicable when this Gaussian profile, okay, the radius of this Gaussian profile is larger than E, because if it is larger than E, it means that it is no longer inside the sphere. It is located at outside of the sphere. So these are the limits of Y region. Okay, this will be the um, reference for region 1, where the radius of the Gaussian profile is lesser compared to the radius of the spherical. Okay, now let's look at these are the formula given that I have mentioned earlier. All right, and we know that electric flux density, which is dr, is equals to q over 4 pi r squared, where we have derived in previous slide, right? And from this we can rewrite q is equals to dr 4 pi r squared, right? So what left behind? Left behind is ts. Okay, left behind is ts. So from here, okay, we can say that this q, okay, this q, it will be dr 4 pi r squared. Okay, dr 4 pi r squared, and this ds, okay, is equals to integral rho v, okay, which is here the charge density, okay, the which is rho v, okay, rho v over dv. And what is our dv? The one that we deal with is spherical coordinate. So if we look back to our previous note, what are the formula for dv in terms of spherical? It is r squared sine theta dr d theta dv. Okay, these are the formula from what we have derived or discussed in last topic, right? So from here, we can see that there are three variables involved, which is r, theta, and phi. So you have to make the limits for each of the variables. So for r, it will be from r equals to 0 to r, and from theta is theta equals to 0 to pi, and from phi equals to 0 until 2 pi. Okay, and you if you solve this equation, yeah, if you solve this equation, you will get that the electric field density at region 1, which is inside the sphere, is rho v r over r3 at r direction. Okay, at r direction. Okay, now you have solved the first part of this equation. Okay, so you need to solve another part of this equation, which is the outside of the spherical. Okay, now this is the spherical. Okay, this is the spherical. Inside the spherical, of course, it will contain electric flux, right? So there is an electric flux inside here. Okay, I put it as dot 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 here, and then what I have to decide now, I have to make the Gaussian profile. But before I make Gaussian profile, I should mark where are the density, electric field density location. So I put it as here. This is my electric field density, and I will draw my Gaussian profile shape here. I make it a circle as well. So now the radius will be, I make it the radius from the Gaussian profile, from the center to the Gaussian profile, as r as well. Okay, as r as well. However, okay, however, there is conditions or limitations. Okay, there is a conditions, there is a rules for this solve, okay, for this methods, yeah, for this calculation, where these are, okay, these are should be larger than a. Okay, this calculation will be not true or will be not applicable if r is lesser than a. Okay, so if r lesser than a, it will be inside the sphere. If r bigger than a, it will be outside the sphere. So when r is bigger than a, which is outside the sphere, the electric flux will be only contains inside this area only. There will be no electric flux here. Alright, so electric flux area will be only limited by this sphere. Okay, here there no more electric flux, because when it is outside of the area, it is outside from the electric source, okay, there will be no more electric flux, right? However, for this, since that the electric flux, since that the area is inside the sphere, and I make the region of electric field density is at this point, so the flux that I will consider is only inside this Gaussian. Okay, however, for this it will be the whole shape, but it will not reach this Gaussian profile. Okay, so please be careful for that. All right. So now our dr, okay, our q, yeah, from this electric flux density, it will be same, yeah, dr for pi r squared. However, for this part, yeah, however for this part, it will be 4 over 3, okay, rho v will be 4 over 3 pi a 3. Why a cubic? Sorry. Why a cubic? A cubic is now will be the radius of volume charge. Okay, a cubic will be the limit of flux that contained inside this shape. Okay, right? Because the flux is only located within this sphere shape, right? So it should not be r squared anymore. Okay, it should not be r. Oh, sorry, it should not be r, but it should be a cubic. All right. So if you solve this equation, you will get that at D2 region, which is outside this sphere, you will get rho v a cubic, yeah? And this 4 can be solved, yeah? Can be cancelled to each other as well as pi a cubic over 3r squared at r direction. So what are the difference here? You can see if the what if the electric field density is located inside the sphere, it will be when r is increased, okay, when the radius of the sphere is increased, the electric field density also will increase proportionally. Okay, will increase linearly. Okay, sorry, will increase linearly. However, if the electric field density is located outside the apa, the spherical or the shape, okay, it will, if the r, okay, when the if the r, okay, of the if the radius of the between the electric field density to from the point charge is increased, okay, if the r is increased, okay, when r is increased, the electric field density will decrease. Okay, and if you draw a graph, how it will be, okay, if you draw a graph, how it will be, this will be the field distribution. Okay, this will be the field distribution. This will be the r, okay, where the length of the distance of this electric field density. Okay, so at this is region 1, which is located inside the sphere, and this is region 2, which is located outside the sphere. So the shape, the graph will be increase linearly, okay, when if the electric field density is located within the shape, it will increase linearly. However, if the electric field density is located outside the shape, it will decrease, it will decay. Okay, it will decay. All right, so this, if you are plotting a graph lah, okay, so this will be limit by the, so this will be the limit, this will be the limit, oh, why I can't write, okay, a will be the limit, okay, the radius of the sphere will be the limit of these changes, yeah. So it should be lesser than a if you want to increase the electric field uh, uh, what linearly. However, if you want to decay the electric field, the r, yeah, the position of this electric field should be far from the radius of this. I mean, should be larger compared to this spherical size. Yeah. So I hope by now we already have a big picture. Okay, you have already clear about Gauss law and also electric flux density. Okay, I would advise you to have additional reference as well. Okay, so that you can you understand more. Okay, try to find other sources as well. Okay, and then please do the practice that I have included in your e-learning. Okay, if you have any questions, if you have any problems, please inform me and get back to me, right? So that can discuss it through class. And don't forget to do the exercise, because I will discuss that through during class as well, right? So thank you, and see you on Wednesday, inshallah. Thank you so much.